Hello everyone, welcome to our new video. Now we will continue with chapter 5 in the finance lecture series. So here we have the uneven cash flows, and we have seen the even cash flows in the previous video. We have talked about how to calculate the present value or the future value of an annuity. So if we have the annuity that is given, let's say, for 5 periods or 5 years, let's say, you can think this as uh, basically evenly distributed time periods. And this interest rate is given as 12%. Suppose we have the cash flow that we receive as $100 at the end of each year until this fifth year. And then on the fifth year, we receive this $1,000 plus the regular payment of this $100 together is $1,100. But we might also have irregular cash flows, especially if we have invested in a project. Our cash flow that is generated from this project might be uneven. Like first year, let's say we get $100, the second year $300, 300, and 500 at the end of the fifth year. And again, we have the same interest rate. So in this type of irregular cash flow, how can you calculate the present value of this cash flow? Actually, it is very similar to what we have done in the even cash flow, but the difference is we cannot reduce it in a closed form formula. We can still use the same summation idea where we have, as you see, the cash flow, how much we receive as cash at the end of first year, second year, and at the end of the nth year. So we just calculate the present value of each cash payment that is given with respect to these years or n number of periods. And as you see, we discount 1 period, 2 periods, and n number of periods for the payment that we receive at last. And this can be represented in a more compact form as a summation. And you can see that the difference from our even distributed payments is that we cannot take this out. So this is no longer constant anymore. So we cannot take this term out. So this depends on the time t, okay? Because for each time t, this cash payment is not necessarily the same. So here is the figure that shows us the present value calculation for the uneven cash flow stream, and you can see that we have assumed 12% as the discount rate when we calculate the present value from year 1 to time 0. So basically you will divide $100 by 1.12. Okay, so the first present value here, this is obtained from this 100 divided by 1.12. Okay, so this gives us 89 point something here, and you can continue for the second term. Basically we obtain this as $300. That is, now this is end of the second year, so you are going to have 1.12 squared this time because we have to discount, take it back to 2 years. So that's the present value of the second payment. And you can continue to apply. As you see, 300 that we receive at the end of the third year is actually the present value is smaller than the 300 that we receive after 2 years. So the longer you wait, the smaller present value gets for the same amount of money. And you can add all these together to calculate the total present value of this cash flow stream, basically. Actually, we can apply the similar idea, but this time calculate our future value instead of the present value. So in a future value calculation, instead of going back to time 0, we need to take everything to the future value, and evaluate for the end of the year 5. Okay, so for example, if you start with this 500, which is paid at the end of year 5, so the future value of this is the same itself, because that's already the money that you will need to wait for 5 years to get. And then you have this $300 that you receive in the end of the 4th year. So you can calculate the future value by multiplying this 300 by 1 point, the interest rate, that's the 12%. So you can multiply these two to get this number 336 here. And similarly, you multiply 300 by the square of 1.12, and that gives you this number 376. And as you continue, basically for the second term, you are going to need to multiply with the third power of 1.12. So basically this 300 that you receive, that becomes 421, that is obtained by multiplying with 1.12 cube. That's the cube, because we need to go forward 3 times, 3 years, and it is compounded by 1.12 to the power 3, and that gives us this number 421. And similarly for this guy, you need to multiply with the 4th power of this interest rate, and that gives us this 100 becomes 157. Okay, now let's talk about the effective annual rate quickly. And this is the annual rate of interest actually being earned as opposed to the quoted rate. So here we are interested in what we are actually earning from this investment instead of the quoted interest rate. And then we have the so-called annual compounding. Basically, this is the process of determining the final value of a cash flow or series of cash flows when interest is added once a year. And as you imagine that you might invest some money in the bank, let's say deposit account, that's the simplest example. And basically, as you earn the interest, you might, if you are not withdrawing your money from the bank, you will reinvest the total amount as it grows by adding the interest rate. It will be compounded year by year. So you will be having the annual compounding, and that's going to increase your interest earning. And we might also have semi-annual compounding, depending on the time horizon that you do this investment. That's basically the arithmetic process of determining the final value of a cash flow or series of cash flows when interest is added twice a year. So in the semi-annual compounding, this interest payment is received every 6 months. So at the end of the first 6 months, actually, so suppose this is the 6 months time, and then you have the 1 year time, of course. and there is the 1 year. So basically it's just like you are reinvesting at the end of the 6 months for another 6 months time period. But when you do the reinvestment, your interest is already added, so that will give you a bigger, compounding effect. So the more frequently we do this reinvestment, the interest earnings are added onto our initial capital. So our money is growing multiple times as we compound during the year. And here is the demonstration with a diagram. Basically, in the first case, well, in both cases, first of all, we invest $100. Okay, and basically the first case is the directly annual rate. So if we have just invested $100 and we are going to wait for 1 year, one year, then that's going to be here 10.25% given. But if we are doing the semi-annual compounding, we need to calculate the effective basically annual effective annual rate, yes, according to this equation given here. So in this equation, what do we have? Actually, it's not a very complex formula. So you have the interest rate, that is the nominal interest rate for basically m number of compounding periods per year. And then this compounding frequency m is used to divide this interest rate, the nominal rate, by m. And then we need to compound it m number of times. For example, this m can be the, if this is the monthly, if we have the monthly interest rate I, then we are going to divide it, this n, basically our m, sorry, will be 12. So we will divide this nominal interest rate by 12 first, and then take the 12th power and subtract 1. So this gives us the equivalent rate for 1 year. In other words, effective annual rate tells us the corresponding interest rate if we are, doing this investment for 1 year, what would be the return that we make, from this investment. So here this I nom is a nominal interest rate expressed as a decimal, and m is the number of compounding periods per year. So for example, let's say the nominal interest rate is 10%, but with semi-annual compounding. So this 10% is for semi-annual compounding. So we have the nominal rate as 0.10 and m equals to 2. So if we put things back, we can calculate the effective annual rate that gives us basically 2 times, we can reinvest one more time at the end of the 6 months time period for this example. So you have the nominal rate divided by 2, and we take the square minus 1. So the effective annual rate is 10.25%. So if we invested $100 at the beginning, basically we will make $10.25 as the interest from this 1 year investment. Another point is we might have fractional time periods. Suppose you deposited $100 in a bank that pays a nominal rate of 10%, but adds interest daily. So now this is daily. Then you can calculate how much would you have after 9 months, And basically the answer here is going to be, there's a dot here, $107.79. Okay, so basically we just do the effective, we can calculate the interest rate first. That is the nominal interest rate, 10% per year. That's divided by the number of days. So this gives us the basically interest rate, periodic rate per day, since this is going to be daily compounding in this example. And the number of days is 9 over 12 times 365. And this gives us 0.75 times 365, and basically 274 is what we get. So the ending amount is calculated by multiplying this $100 with the per day, basically interest rate that corresponds here given, and then to the power of 274, and that gives us $107.79. And as you see, this is by calculating the number of days for this 9 months period, which we basically approximated a little bit, because 9 months we have total 12 months, of course, and then 9 months out of these 12 months we multiply with this 365 days per year, and that gives us roughly 274 days, and that is what we used in the compounding here. Finally, we have another technical term, and that's called as the amortized loan. Basically, it's the special type of loan where the loan is repaid in equal payments over its life. We might see some examples of this later on. So that's all for this video. Thank you for watching.